So good morning, Dr. Patro.
Good morning, Dr. Saxena.
Thank you very much for being with us today for this FDP. So I would request to Prachi, please introduce Dr. Patro to our participants so that we can start this first session of today's, which is the fifth day of this International FDP. Prachi, please.
So, a very good morning to all. I welcome you all for the first session of the day, which is going to be delivered by our keynote speaker, Dr.Debdutt Patro. He has done his PhD in Materials Engineering, IISc Bangalore. He has 13 years of experience. His fields of interest or expertise are materials and manufacturing, tribiological performance of materials. He holds a PhD in materials engineering from the Indian Institute of Science, Bangalore. He is also a certified Six Sigma Green Belt and TRIZ Inventive Problem Solving Level 1 and 2 expert. As a product specialist at Ducom Instruments, he collaborates with the academia and industry to establish knowledge partnerships in friction and wear evaluation of materials. As a subject matter expert (SME) in materials tribology, he hosts workshops and specialized courses on contemporary challenging topics such as high temperature tribology and biotribology. He served General Electric Global Research and Development Center for 10 years in the Manufacturing and Materials Technology Organization. During his period, he conceptualized and matured several technologies across diverse applications such as friction-resistant MEMS devices, designing high-temperature materials for gas turbine applications, novel designs for low-cost desalination of seawater, reducing manufacturing defects in wind blades. He has been granted 2 patents and several management awards for business impact, the most recent being the ceramic matrix composite blade for the GE9X engine, the largest commercial engine ever built. He has published several articles related to high performance materials and test method development. Now, I would like to hand over the talk to Dr. Debdutt Patro. Please, sir.
Thank you very much for the kind introduction, Prachi. So, good morning, everyone. Let me quickly jump to the presentation. Is my screen visible?
Absolutely fine.
Okay, thank you very much. So, Ducom Instruments, our company, we have been around for 40 years in India, and we call ourselves the tribology characterization experts. Tribology here being study of the friction, wear, and lubrication of materials. Outline of the 1 hour or slightly more than the interaction session. We'll start with a brief introduction, then quickly jump with the introduction. We will quickly jump to several industrial case studies where we use material characterization methods to understand the performance of different materials. We will also highlight the importance of repeatability and reproducibility of test data, scientific data, and finally conclude with some future looking statements and some ideas we have on how we can convert scientific labs from what we knew earlier to make them more future ready. How can we get a lot of 4.0 technologies inside our day-to-day working culture when we do science, and use them to make our labs more productive. So tribology being the study of friction, wear, and lubrication, it is very diverse. It touches upon a wide variety of applications, industry segments. So on the top left, you can see it's a gear. It's a very common mechanical element, and you use lubricants. On the top right, you see a more human interface, which is where you start looking at implants and things which go inside the human body, and these two have to last for quite a long time. So that area is called as biotribology. On the bottom left, you would see steel rolling mill, and there too there's a lot of high temperature materials and interactions of materials during the rolling process. So this would be another extreme of temperatures exceeding 800 degrees. So that would require evaluating materials at high temperatures. And finally, on the bottom right, you see something which is on the solar panel. Again, solar panels are supposed to be efficient, use photovoltaic to generate, electricity. But over a period of time of their life cycle, 20-25 years, a lot of the solar panels get eroded, the surface gets degraded, so the efficiency comes down. So the wear and degradation of materials because of exposure to environments which are, let's say, in the solar panel or in the industry or even inside the human body, eventually leads to these materials degradation and efficiency loss, and in the worst case it could also risk safety. So where does the word tribology come from? It comes from the Greek word tribos, which means rub, and ology means generically the study of any subject. So tribology is basically the study of things that rub. If you go back into history and look at where this study, or where we started understanding tribology, we started using principles of tribology much before the scientific understanding. So this is a painting from the 2400 BC, and if you see, they used to drag these huge blocks of rock and build pyramids. And remember, this was in Egypt, in the desert, and dragging things on the desert is fairly difficult. So people started using hot oil or some kind of lubricant to reduce friction and make it easier for them to pull. So at that point of time, they did not know about friction, but it was mostly experience. Of course, before this, the very first event which happened a million years ago was primarily, the fire. So taking two pieces of rock, rubbing them, actually generated heat because of friction, and that lit some dry pieces of wood and leaves, which is what enabled us to control and manage fire and evolve from being cavemen to a more civilized society. So with a lot of experience over several thousands of years, it was only 500 years ago that Da Vinci, who among other things, being a very great painter, was also a very good engineer. So he built a lot of scientific principles and sketches, and this is from his own work, which shows how you can measure friction between two surfaces using simple geometries. But more importantly, he also told us how you can design things which you see here as ball bearings, which can convert sliding friction into rolling friction, control, design this for more industrial machine technology. It was not about 60 years that late Dr. Peter Yost, who actually founded what we know as industrial tribology. He was asked by the UK government to see how we can reduce the friction or the energy losses in industrial systems. So he chaired the committee, and he found that he realized and submitted a report based on his findings that if we are able to control the amount of friction, reduce the amount of wear, we could save a lot of energy. That could reduce, give us more time on our resources. It could also lead to lower emissions. So that kind of laid the foundation for modern tribology as we know it now. So if we summarize all what was covered in the slides, so we're looking at some kind of disruption on our understanding of this subject on the y-axis, and the timeline is on the x-axis. So starting with human evolution from the cavemen with control of fire, industrial evolution with Dr. Peter Yost, and now we are in the sustainable evolution where we want to grow in a more sustainable fashion. So the next thing comes is where to from the sustainable evolution period, and that's where we will cover towards the end of this talk something on how we can use data, sensors, the internet 4.0 technologies to really reimagine how science and tribology should be like. So at Ducom, we actually embody this spirit, and we use tribology to build solutions, to build products, to offer services which actually change, or we believe will change the world. Quick background on our company. So we are based in Bangalore, in India, and in the last 10 to 15 years, we have established offices in US, at New York. In Europe, we have an office in the Netherlands. And last year, there was an office which was opened in Malaysia, inside the University of Malaya. We build a lot of tribometers. Given that tribology is a very diverse topic, it covers high temperature, it covers lubricant, you can also look at things happening inside the human body. So we build a wide range of tribometers, and all of them have a lot of sensors in order to capture data during the test. And these sensors are in fact connected to a digital platform which make them smart, much like your smartphone or a smart fridge. So all of these sensors actually help you monitor and remotely what's happening on the tribometer. So these are a wide variety of tribometers. I don't want to cover it, now it's not the intent of the talk. And you can get a lot more information on our website on our tribometers and technology, as well as reach out to us, on the above email address. So that was a quick introduction. I will move on to the next section. So this will be slightly long, this segment, and we'll cover refresh some of the basic principles of tribology, friction and wear. And then using those principles, we'll see a few case studies where we can use that understanding to set up a problem, and also how we use material characterization techniques to solve and come to some scientific insights on these problems. So this is a simple chart from a wear control handbook by Arkard. It's very powerful in a sense that it captures pretty much all the elements of tribology on one slide. So if we focus on the left side and start from the top, we look at interacting surfaces or surfaces which rub against each other. So the statement goes as all engineering surfaces are rough. Even though we get super fine surfaces, they still are rough, and they are contaminated. So there are no surfaces which are truly uncontaminated or clean, there will be some extent of contamination. And when these rough surfaces which have contamination rub against each other, they rub against asperities which are there on the surface. And when these small asperities contact each other, you get local stresses which are fairly high. And when these local stresses which are fairly high exceed some of the material properties which are very surface specific, you could get failure, which could be fatigue, but you could also have friction being generated when these surfaces or the asperities rub against each other. And when you exceed certain strength parameters of the material, you could have those asperities removed and get wear. So contacting surfaces rubbing against each other at asperities would eventually lead to these different modes of degradation, which is failure, friction, and wear. And one way in which we can mitigate is by adding some form of lubricant. And the lubricant eventually can fall into any of these categories: solid, liquid, or gas. So solid could be, let's say, poly PTFE or Teflon is a very commonly used solid lubricant for bush bearings. It provides a very smooth, lubricious surface, which makes it easier for parts to rotate against each other. Liquid is, let's say, the engine oil which we put, the lubricants which we use, greases which we use, even lip balms we use when we talk and our lips become dry. We also use the lip balm or lip jelly in order to lubricate such that we are able to speak properly. And finally, gas. So there are in advanced machine elements, people also use aerostatic bearings, gas foil bearings, where the surfaces are supported by a thin film of gas, so they don't rub against each other, because the gas provides the support and prevents these asperities from touching each other. So that is a quick refresher on, let's say, tribology, friction, wear, and lubrication. Now, if we look closely at a schematic of what happens when these surfaces rub, and this is the image on the bottom right of this slide, you can see a top surface and a bottom surface. And if you zoom in really close, you see that there are asperities which are touching at certain points, and that is where you get a lot of high stresses and tendency for wear happening. In between these two bodies, there is an arrow which indicates to a third body. So this third body is could be a very important element in this entire study. It can control, let's say, the third body could be a solid, liquid, or a gas, which is introduced in order to prevent wear and friction. More importantly, you could also control and engineer the third body, so that it evolves during the process of friction and wear. And we will see how the third body interactions is actually one of the most important elements in tribology when we go over to case studies. Now we'll quickly look at some of when these asperities are contacting against each other. There are two scenarios. One is where there is solid to solid contact. Then you get wear, dry wear, and then we will have liquid, which is put as a lubricant, and there you will have liquid or liquid lubricated wear. So these images show the dry wear conditions. So you would see that the surfaces rubbing against each other, and if in case there are certain debris or sand particles, let's say, which come between these moving surfaces, they can act as abrasives, and wear out both the top and the bottom surface. In case there are no other external media, but the surfaces are dry or rubbing against each other, then you would get adhesive wear. So whether there is a third body as a sand or there is no third body, the way one would set up and look at a test technique is called pin on disc tester, ball on disc or a pin on disc. This is one of the most common instrument techniques or test methods for looking at friction and wear of materials. Pretty much 90% of all problems can be solved looking at, in the lab level, solved or understanding developed looking at a pin on disc tester. Next, you come to abrasive wear, where you have got some kind of dry sand or abrasive, and when that rubs, like an example is in the mining industry, when you are doing digging, excavation, or taking out ores, you are not rubbing two surfaces, but you are taking your, the machine element or the excavator bucket and mining out from the ground. That causes some kind of abrasion between the material which you are trying to extract and then the steel part, the bucket part or the excavator. So there you don't have two surfaces, but you have got the part on a surface, and that is studied usually using the dry abrasion tester. Now, wear can also be not very unidirectional like the top surfaces, but also more vibratory in nature. So typical machine elements will always have some form of vibration. Nuts and bolts, joints, mechanical fasteners, all of these elements will have some kind of vibratory or oscillatory motion, which is called as reciprocation or fretting, depending upon the amplitude of the oscillation. And that introduces a different wear mechanism because the part is rubbing against each other, over and over again, millions of cycles. These wear, that type of wear can be studied by something called as a high frequency reciprocating tester. So depending upon the types of wear you see between different material surfaces, the nature of motion, and if there is a third body present or not, one could look at different techniques for looking at these problems, and eventually the materials which we want to deploy or use in these conditions have to be tested using laboratory scale test methods. Now, we have looked at dry wear. We could also look at lubricated wear, and this is a classic example of something which is called as a Strybeck curve. It shows you on the top that the coefficient of friction, which is the green curve, is not a constant number. It varies depending upon the regime in which your machine element is operating. For example, if you are operating at very high speeds, which is on the right side of this chart, so you are having high speeds, it's like a hydrodynamic, a classic example is a hydrodynamic journal bearing. So there are cartoons on the right of the slide which shows you what are these regimes of lubrication. So hydrodynamic journal bearings operate on complete fluid film. So there is a continuous film between the surfaces. So even though the surfaces are moving relative to each other, the asperities are never contacting. And if they don't contact, you will not get any wear. The friction is also very low because you are using a fluid which is a very low viscous, it's easy to shear. Now, as you start decreasing the speed or increasing the load, what would happen is these two surfaces would start coming in contact or approaching each other because of the higher load or the lower speeds. Then you go into a regime called regime B, which is mixed lubrication. There, in that condition, you start getting some of these asperities contacting against each other. So you have some pockets of fluid and you have got some solid contact, and the friction coefficient increases. And finally, when you are on the extreme left, so the loads are very high or your speeds are very low. An example is, let's say when you are starting an engine or you are starting a bearing, right? There is no fluid film initially, so you start the solid to solid contact, and there you get very high friction coefficient. So for lubricated conditions, one cannot assume that the lubricant is going to reduce the friction all the time. It also matters a lot on which regime of lubrication you are in. If you are on the extreme right, yes, your lubricant is doing a very good job. If you are on the extreme left, you might have put a lubricant, but you are still having solid to solid contact. So one really has to consider the lubrication, efficiency of lubrication with respect to the regime of in which these machine elements operate. So quickly to summarize that, so we covered the tribology, the basic mechanisms, whether it is dry wear, whether it is lubricated wear, and even in dry wear there are several categories of dry wear. In lubricated wear there are several regimes of lubricated wear and friction. So understanding all these regimes and mechanisms is very important, because when we start conducting material tests, lubricant tests in the lab, we are better, we have more knowledge on what these experiments are and how to interpret the results. The second point which is important is there are certain characteristic operating conditions which we want to capture. For example, stainless steel is used both, in the in steel rolling mills. It is also used inside the human body. If I want to understand friction and wear of stainless steel inside the human body versus in the steel rolling mill, I cannot use the same test method or approach because of the operating conditions in which these materials would see. So then we have to add another element of certain characteristic test conditions. Now summarizing all that, I will highlight 3 case studies, primarily addressing some of the broad challenges which we face. So one is climate change, a lot of emissions. We want to reduce emissions, we want to reduce the carbon dioxide emissions. So there are certain technologies which are used for encountering that. We also want to have a healthy lifestyle. People are living longer, they want to live longer, but also they want to live healthier. And finally is energy efficiency, so energy generation, energy usage. So there will be 3 case studies presented covering all these aspects, and also looking at some of the fundamental friction and wear mechanisms which we understood in the previous slides. Climate change, transportation is a big industry, and there's 25% or 30% of the greenhouse emissions comes from transportation. 10 to 15% comes from mining. So there is a lot of interest in making sure that how we can reduce the emissions of greenhouse gas, and most of that has to do with reducing friction. If we reduce friction, we get more of our energy converted into motion, and we don't waste it up otherwise. There are estimates which say that a 30% reduction in friction would give you, 1,500 million tons less carbon dioxide. And to put that in perspective, every car, let's say our cars which we use for personal use, in 1 year it emits 5 tons of carbon dioxide. So if we reduce friction by 30%, we can take almost 300 million cars off the road, or an equivalent of the emission of 300 million cars off the road. So these are huge numbers, and that also is a very big motivation to reduce friction in the transportation systems. If you look at a transportation system, which is an internal combustion engine, which we are still using, we are obviously transitioning to electric vehicles and also hybrid electric vehicles, but we still have got at least next 10 or 20 years before the complete transition happens. For the time being, there is a lot of focus and drive that even in internal combustion engines can we improve the efficiency and reduce the emission. And one of the biggest areas of where you get a lot of friction loss is this piston ring cylinder liner. So the piston ring cylinder liner, if you see here, and because you add engine oil, it lubricates. So we will use this as a case study for lubricated wear. When it operates in a reciprocatory motion, so it goes from top dead center to bottom dead center during the entire combustion cycle. And in case of the lubrication regime, it goes from boundary to mixed and also hydrodynamic. So if we have to set up an experiment and study if a lubricant is good in, or it can reduce friction in a internal combustion engine piston ring and cylinder liner, it has to explore all these regimes. Now we have picked up two candidates for evaluation here. One on the left is called as a low viscosity engine oil. The viscosity is lower. And on the right, you have got high viscosity engine oil. An example of high viscosity engine oil could be your 20W50 oil, which we put in our vehicles. Low viscosity engine oil is 10W30. And there are mathematical expressions which say that the power loss is proportional to the viscosity. So lowering the viscosity helps reduce the power loss and thereby improve the efficiency. Again, we go back to a pin on disc test, but now because we have to cover different regimes of lubrication, we set up a test where the speed and especially the speed changes. And what I mean by that is, on this plot, if you see, there is the white curve, which is the speed, and then the green is basically the friction, which is measured between the two surfaces in the presence of a lubricant. The speed during this test, which lasts for 30 minutes, starts off at 1500 RPM between the parts and decays to around 100 RPM. So this is intentionally set up so that we can see the entire regime of lubrication. This is the test data from a tribometer with two different oils. So the blue one is the high viscosity 10W40. The yellow one is the low viscosity engine oil 5W30. And as you see, the Strybeck curve, which tells that the friction coefficient is not a single value, but it depends upon what is your operating condition. You can see that data from the machine suggesting a typical Strybeck curve. More importantly, you can see that the yellow curve is 60% lower than the blue curve. So the friction coefficient between these two oil difference, the difference between these two oils is close to 50-60%. So 0.08 and 0.04 from this test data. So immediately it gives you an indication that going to lower viscosity engine oils is beneficial, not only in one regime of operation, but you see that gap between these two curves is fairly consistent across this entire operating regime, which is the x-axis. These studies also have been translated to the field. So people have used, there are many studies from reports in Europe where these engine oils have been changed in school buses, public transport systems, and tests run. These tests referred to as fleet tests, and we get around 0.5% fuel saving, from the fleet tests. And when we run the laboratory tests, you get around 0.4%, so 0.37, 0.4%. So it also gives you a lot of confidence and clarity that simple tests in the lab, if set up and done correctly, can also give you a lot of insights on how these how the improvements can be in the field. So the first was an example of lubricated wear. Now we will go to another important thing, especially in India, in the context of India. It's called as, since we are still heavily reliant on coal as a major source of power generation, and India is a signatory to the COP, so Paris Climate Change Conference Treaty, where we want to reduce the emissions from coal and improve the efficiency of our thermal power plants. So in that context, what this Department of Heavy Industry is doing is part of the National Clean Coal Mission is to build advanced ultra supercritical power plants. Now, advanced ultra supercritical power plants, if you see on the right, operate under regimes which are very, very severe compared to traditional power plants. So the temperatures can go as high, steam temperatures can go as high as 700. The pressures can be 300 bar. So the materials and infrastructure has to see a lot of aggressive conditions. The benefits are you get a significant improvement in the efficiency, up to 45%, which is very good for traditional power plants, and a significant reduction in the carbon dioxide emissions. So improving efficiency and reducing carbon dioxide emission also means that you have to operate these power plants and the infrastructure at higher temperatures. One form of failure which is seen when you start running them under these conditions, this is a typical gas turbine where you do the combustion process. So you got one combustor and you got a liner, and these parts you see they are it's actually mated against each other. Because of the combustion process, there is a lot of vibration and they rub against each other, and when they rub, you see the kind of damage which happens. And when the critical tolerances are exceeded, the combustion efficiency comes down. So excessive wear can reduce the combustion efficiency. So that is a problem. How do we address it? So we have to now simulate conditions of very high temperatures and surfaces rubbing against each other. So we rely on, let's say, setting up an experiment. This is a video. And you see basically two red hot surfaces rubbing against each other. So this is a reciprocation. And during this entire process, we are measuring the temperature, we are measuring the friction, and we are also measuring the wear. How did we set up the experiment? So we took certain materials which are called super alloys or mnemonic alloys. These are the advanced materials which will be used in the supercritical, advanced ultra supercritical power plants. There was certain load applied, around 100 Newton, and there was certain stroke. The important thing is we ran these experiments starting from room temperature all the way up to 900 degrees, much beyond what the supercritical power plants would operate. Because being in the laboratory environment and having those capabilities, one can also look at beyond, some other beyond capabilities. We ran them for 25,000 cycles and also additional 25,000 cycles. So this is the test data which we got at the end of the experiment. And on the y-axis, you actually see friction between these surfaces which are rubbing. And on the x-axis is the timeline or the number of cycles going to 25,000. Starting from the top, the friction coefficients are 0.5 to 0.6, and these are at temperatures up to 300 degrees. As soon as you start increasing the temperatures beyond 300 up to 500 and 700 and 900, the coefficient of friction drops dramatically. From 0.5 to 0.6, it drops to 0.1. So these surfaces at high temperatures, are less resistant, to rubbing against each other. We also measured the wear, or how much material was removed from these surfaces as a function of temperature. Y-axis again shows how much wear has happened in volume loss, millimeter cube, as a function of temperature. Again, the same trend. If you start at ambient, which is on the extreme left, is very high wear, and when you go to higher temperatures, exceeding 700, you get very low wear. So surprisingly, when you take some of these advanced materials and rub against each other, as temperature increases, the friction and wear drop down dramatically. So these are some of the posts. So one can also do a lot of characterization to understand material behavior. So you start observing the materials, and you see very shiny surfaces, which indicates that this is, so shiny surfaces are typical of metallic nature. As you keep going to 900, you see the surfaces have become dark. After rubbing, the surfaces have become dark. So there is some kind of material on the surface, and this is the third body which forms. So typically what happens is, and this is some EDX results to show what are the materials, or what is the composition of the material on the top surface. So you see that the red graph, the red bars here at 900, and that is for oxygen. So the levels of oxygen actually are fairly high when you go to high temperatures. So the material starts oxidizing, and when they oxidize, the initial metal to metal contact is prevented. There is a third body which comes in the contacting surface, and that reduces friction and wear. So quick summary of this test. So at high temperatures, some of these mnemonic alloys which are proposed to be used, they show low friction, low wear, and this is because of the in situ formation of these tribo layers, third bodies, or glazes. These oxides are highly beneficial in gas turbine components, and they also help us find out or discover new materials, identify new coatings which we can apply to reduce friction and wear even further, all from setting up a simple experiment in the lab. Coming to the last case study here, and this is on biomedical devices. So Kalam Institute of Health Technology is the coordinating center for a lot of research areas in medical technology, and this is from their website. They have got a national research priorities in medical technology, and some of the domains or the technology areas in connection with tribology or friction and wear. So on the left, you see the imaging, the diagnostics, which could be either X-ray or in this case CT. So they use a lot of bearings, and the technology for bearings is also one of the thrust areas. On the right are implants which go inside the human body. They could be hip implant, a knee implant, or dental implant in case one does not have teeth. And the challenge there is to make wear resistant and infection resistant materials and designs. So in that context, can we identify these materials? And if we identify these materials, can we identify how we can set up a test in the lab? How can we know if these materials are doing or will perform better if they are introduced into implants? Case study is one of the dental implant. So a dental implant typically has